Another optimization problem. We're going to try to build a rectangular pen of maximum area with a limited amount of fencing. So we've got an exterior wall that we're building the pen against. So we don't need to worry about one of the four sides of this rectangle because that's going to be a wall that already exists. But we do have to worry about the other three walls. So let's say that one wall that is already there. That's the wall that we don't need to build. Then we have three walls that we have to build with our fence. And it's a rectangle, so we've got whatever this length is up here. We'll call it X. Same length down here. Call it X again. This vertical length, we don't know how that compares to X, but we do know that that new value, Y, is going to be part of the perimeter of this pen as well. So, we've got a certain amount of fencing to deal with. So this is going to be our constraining equation, I guess we can call it, where we have x plus y, or 2x plus y, represents how much fence we have to work with. And 2x plus y equals 100. That's how many feet of fence we have. So this is a relationship between x and y. If I pick an x value, then I know what the y value is, or vice versa. But we're not trying to maximize the perimeter. We have that fixed value of 100 feet. What we're trying to do is maximize the area, because we want to fit as much as possible in this pen. So let's talk about what the area formula is. Well, it's a rectangle, so we all know that the area of a rectangle is x times y, or length times width, or whatever you want to call it, base times height. And that's a equals a product of two variable expressions, but they're different variables. But that's okay, because we know that y happens to equal 100 minus 2x. So that means that a equals x times y, but if y equals 100 minus 2x, we'll just replace the y with 100 minus 2x. And if we're trying to maximize a, then we just have to take the derivative and set it equal to 0, like we always do. So the area is a function of x. The function is 100x minus 2x squared. We find a prime by taking the derivative of the first term, derivative of the second term, setting it equal to 0. We find that x equals 25 is a critical number. That is the value where the derivative equals 0. So double check real quick. The a prime line, we've got x equals 25. That's when a prime equals 0. If a prime is less than 25, then we have 100 minus a small number, which would make us positive. And then if x is a very big number, then it's 100 minus a big number, and then we'll get a negative value. So our area is increasing until we get to an x value of 25, and then it starts decreasing. So if we are interested in when the area is a maximum, we are interested in when x equals 25. But the question is, what is the maximum area achievable with 100 feet of fencing? So we have to find the area when x equals 25. So we simply evaluate the area, which is 100x minus 2x squared when x equals 25. You could use any one of these equations, it's fine. So we have 2500 minus 625 times 2, 1250. 2500 minus 1250 is 1250. And since we're measuring distance in feet, the area is measured in feet squared. And that is the largest area that we can achieve using 100 feet of fencing if one of these sides already exists.